Okay, we covered isoparametric formulation, quadratic elements, higher order interpolation, and today I will cover a new topic, beams, and I'll move with that. Finite elements for beams. So typically beams will be slender structures that can be used to model 3D solids, but these 3D solids are slender. Typically, they can be non-uniform cross-section, but the cross-section has to be small compared to the length of the beam, of the part. And in this example, I have a bridge, and then I have a tower. But these are civil engineering structures, but you can also find them in aircraft and many other components of that we see daily in real life. So the first one that we'll be discussing today is 1D Euler Bernoulli Beam, which I covered a little bit about the fundamentals maybe the second week of class. I'll revisit this a little bit with you. 1750s Euler Bernoulli, looked at this modeling approach, a simplified approach to the problem by representing a beam, in essence, that represents the behavior of the 3D solid. And it only depends on the x-coordinate. You can see here, it only depends on the x-coordinate along the length of the beam. This is assumption that Euler Bernoulli made, this particular assumption where the normal remains normal after deformation. So basically the cross-section remains normal to the neutral axis after deformation. That assumption is really true for very long beams. So if you have very long beams in the order of t over length of 1/15 or so, that's a good assumption. Okay. And then we looked at the distributed loads get reacted by a moment and a shear also. Okay, and then we went through the derivations, force equilibrium. We took a little box of element. We said, okay, there's a moment here, shear here. And with that information, we developed the force equilibrium and the moment equilibrium, and we came up with two equations here, shown here, which we went through already, and it's also covered in your mechanics of material course. And we came up with this relationship for moment and the distributed force. Okay, so this is just more of an overview of what we covered already, and also covered extensively in your mechanics of material course. We talked also that this cross-section remains normal to the neutral axis. That's a fundamental assumption. And what does that mean? If the cross-section remains perpendicular to neutral axis, what is really happening? What is the implications of that on the strains? If there's no change in angle, it means that the transverse shear is 0. Is that true? The shear that describes this little cube here does not get distorted. You have no distortion of that cube due to deformation. Is that true? Yeah. So this assumption that he made actually works out. This assumption he made proves, in fact, that his assumption works out. If you were to calculate shear deformation due to this deflection assumption, you will find that it does work out. You will get basically 0 shear, transverse shear. So we cover that. We talked about what this moment represents in Euler Bernoulli beam theory, and we found that moment is related to the stress in this manner. We also plugged in what stress is in terms of modulus and strain, and we found that I have this relationship. And since I know the strain, which is really the curvature, remember the curvature of the beam, we talked about that. Then when I plug that in here, now I have y times y integral over dA, and that gives me the inertia. So I have EI W double prime. So now I know my moment in terms of the deflection, transverse deflection. So moment is related to the curvature of that beam. Okay, so we covered this also. And then we plugged in this relationship that we just derived into the Galerkin equation, and then we found the equilibrium equation for Euler Bernoulli beam. Okay, I also did this using the total potential energy, and then we worked the steps, and I showed you how basically by minimizing the total potential energy, I get the weak form, which is the weak form that you get by forming the weighted residual for this. And I'll show you what we've done before. So we took the differential equation, and then we multiplied it by a weight function v, right? So this was your residual function. We integrated this over the domain. We made the error orthogonal to each of the weight functions. And the next step is that we lowered the continuity requirements. Because if I wanted to use strong form Galerkin, then I need a higher order of continuity requirements, remember? And I also have to satisfy all boundary conditions. So the idea was to take this fourth order differentiation and bring it basically to half, to 2, and share the derivative with this weight function. That way I have lowered the continuity requirements, and now I only have to satisfy the essential boundary conditions. And so with that, we integrated by parts this term times that, and then we integrated by parts until they had shared it equally. Double derivatives here and double here. Okay? And then we derived the weak form, and the weak form is given here at the bottom. And you realize very quickly that I have v times this term here, and then v prime times this term here. And by looking at this, we also notice that this will tell us what kinds of essential boundary conditions we will have in the problem. Because v, and I told you this already, that we're going to focus your attention to the v's to figure out what will be the essential boundary conditions. And so here, we quickly realize that we have a v and a v prime. So I'll switch v prime to w to figure out what is my essential boundary condition of the problem. So anytime I have w specified or w prime specified, that tells me that those are essential boundary conditions, and I know that now. And so anything else will be natural boundary condition. We also noticed very quickly that this was a shear. This term is shear, and this is moment. Okay, that's the moment. And so with that, we developed the weak form. By the way, this is the weak form, so there's nothing more to do. But we did more manipulation just to keep things simple. We also, so then I expanded this. So I made this v. Just called it v, and that's what you want to do in your homework and the different problems. You will call this something. You can call it a variable, because this quantity, when it's given, the natural boundary condition was given, you will substitute the natural boundary condition directly in here, okay, directly in there. So that's why we call it m and v, because maybe they are specified, maybe. And so expanded form, this is the way it looked. If I want to just expand out the boundary conditions, this is the way it looked. We wanted to do a little trick here, so I have a plus sign here. I want to make this minus, so that when I bring all these terms to the other side later on, they're all positive. And to do that, we realize that we have to turn this moment the other way, but everything else stays the same. And then here, the shear has to be turned the other way, and then everything else that stays the same. So it's a little trick, but nothing to be worried about. It's more for convention purposes. And then when you do that, you plug this back in here. What you get is your weak form Galerkin with now you have the V's here, and everything is minus sign with the Q1, Q2, Q3, Q4. And so this is the weak form. It's just a different way of looking at it, but it's still the weak form. And if I plug in what Q1, Q2, Q3, and Q4 are, these are what we had defined. So it's nothing different. I just put a variable there and name there. Okay. So that's the weak form. And now if I want to develop element formulation, right? That's what we're trying to do. We can do that. So the first step, I don't know why this is not showing up. Okay, we'll continue here. So we talked about developing a weak form Galerkin, right? And how do I know which variables here, what are the variables that should be continuous across element boundaries? Because when I develop an element, I want to know what should be continuous from one element to another element. How do I find this out? Sorry? Yeah, but how do I know which nodal unknowns should be continuous across element boundaries? The essential boundary conditions will give me a clue of what are the variables that should be continuous across element boundaries. So in this theory, a beam cannot have a kink. It needs to be continuous across element boundaries. We know that because when I look at the essential boundary conditions, these guys here, right here, are telling me what should be continuous across. So when I look at V and V prime, if I switch that to W, it's just telling me that W and W prime need to be continuous across element boundaries. Is that clear? Yes? Like when we had the heat transfer problem, right? The essential boundary condition was anything specified on temperature. Well, that tells me what needs to be continuous across element boundaries. The temperature needs to be continuous across element boundaries. For the bar problem, we also found that for the bar problem, the displacement was the one that had the essential boundary condition specified to. That means that displacement has to be continuous across element boundaries. Is that clear how you figure that out? Okay, because, go ahead please.
The displacement's like physically intuitive because you just can't have it, but like what about forces? Why can't the forces be discontinuous?
Remember that the question for the video is why the forces cannot be continuous. That's enforced through the natural boundary conditions. For the essential, what we're trying to do is to plug in an approximation function, right, that has unknown coefficients. And these unknown coefficients are the ones now we've redefined it from Galerkin to finite elements to be the unknown quantities at the nodes, right? So those unknown quantities have been related now to displacements. And in this case, we need to relate it to slope. Those are the two quantities that need to be continuous across element boundaries, but also the approximation function only needs to satisfy the essential boundary conditions, right? Those are the only ones that need to be satisfied, the essential boundary conditions. And for that reason, the force may not be continuous across, necessarily. Okay? All right, so this is the weak form Galerkin. We developed that. Now, if I choose an approximation function now, that approximation function, how many unknowns will it have then at each node? 1? 2. How many vote for 1? Raise your hand if you vote for 1. How many vote for 2? 2 unknowns at each node. Why you say that we need 2? Because I have 2 essentials at each side. I have V L and V prime L in one side, and then V0 and V prime at the other side. So I have 4 unknowns now, right? 2 nodal quantities that are unknown at one node, 2 nodal quantities that are unknown at the other node. They have physical meaning, okay? So if I were to ask you, what polynomial do I need if I have 4 unknown coefficients? What order polynomial do I need? Cubic polynomial will have 4 unknown coefficients, right? So if I have a cubic polynomial, I can then use that. I'll just use a cubic polynomial for my approximation function, okay? And my nodal quantities will look like this: theta 1, V1, and then theta 2 and V2. I'll call them that, okay? This is my nodal quantities. Where W sub 0 at 0 is V1, W prime at 0 is theta 1, W at L is V2, W prime at L is theta 2. Now, I can have done this in a natural coordinate system where everything goes from -1 to 1, but since I'm teaching a new concept, I don't want to compound what I've taught you last week with this topic. Otherwise, it would be too much. But you can also do this using coordinates that go from -1 to 1, okay? I just want to not compound things too much, okay? So here, this is my approximation function, right? In weak form Galerkin, what you will have done in weak form Galerkin? In a normal weak form Galerkin. I'll have figured out whether this polynomial that I chose satisfies the essential boundary conditions. That's what I'll have done. Okay? We know right now this polynomial does not satisfy the essential boundary conditions. If I assume that this for this element, these are my essential boundary conditions, right? If I assume these are my essential boundary conditions, this polynomial doesn't really satisfy that. Because if I plug in x equals 0, do I get v1 automatically? No, I get c sub 0. So it's not really quite right. So to do that, I will try to satisfy. So I'll impose the boundary conditions here, and I did it one by one. Okay. And so how many coefficients I have? C1, c sub 0, c sub 2, c sub 3, right? I have to solve for C1, C2, C3, C4 and plug it back in to my polynomial. So everything is now in terms of V1, V2, theta 1, and theta 2. Is that clear what I'm trying to do here? Everybody in the back, if you follow? Okay. Okay, excellent. So if I do that, do you agree that my approximation function now is in terms of all these unknown coefficients? This is what I'll get? Okay. I did that in Mathematica. Okay. I did it in Mathematica. And, but the math looks like this. This is my 4 equations. You know, so I can invert this to get c sub 0, 1, 2, and 3. I can invert it. Then when I get this c sub 0, c1, c2, and c3 in terms of v1, theta 1, v2, theta 2, I'll plug that in here. And now my approximation function will only be a function of this v1, theta 1, v2, and theta 2. Okay. Now, but what I really want to have is an approximation function that has an unknown coefficient times a shape function, plus an unknown coefficient times another basis function, plus another unknown coefficient times another basis function, right? Like you've done in weak form Galerkin. I will not be able to accomplish that in this form, so I need to figure out what is the coefficient to, I really want to know an expression that looks like this. I want something that says v1 times n1 plus theta 1 times n2 plus v2 times n3 plus theta 2 times n4. In weak form Galerkin, this used to be your phi's. Remember? phi1, phi2, phi3, phi4. So we're not doing anything too different. I just call it n now because now the way we're writing it is a little bit different. These n's have shape. They have properties also. And also these unknown coefficients now have physical meaning. They mean something. While in weak form Galerkin, they didn't mean anything. You know, these coefficients here have no meaning. Okay? And also it was difficult for us to make sure that one element to another element, I have continuity requirements met. Okay? So to do that, to find these unknown coefficients, do you agree that if I wrote w tilde as a function of x, do you agree that this will have been in terms of all these quantities now? Yeah? It will not have the C0, C1, C2, C3, right? It will not have any of that. It will be all in terms of V1, theta 1, V2, theta 2. So for me to find the coefficient to V1, what you can do is take the derivative of W that came from here with respect to V1, and you will get N1. Okay? So in Mathematica, you will do that, and you'll get N1, and then you'll get N2, N3, and N4. And I invite you to do it at home so you can see that it works out. There's other ways to do it. There's other ways you can do this, and I taught you other ways to do it. But this is my preferred way because you can get it right away. Okay? When you do that, these are the shape functions you come up with. You come up with basis functions. Okay? Basis functions, but we call them shape functions. These N1, N2, N3, and N4. I can put them in a nice vector format, so I have N1, N2, N3, N4, and then this is my vector of unknown quantities. You agree that this times that is basically what I have at the bottom here? Yeah? Okay. So let's see if this actually makes sense. Let's see if this makes any sense whatsoever. So when I plug in, so this N1 and N2 belong to V1 and theta 1. That's who they belong to. So remember, these shape functions belong to a known quantity which has physical meaning. This N1, which belongs to V1, corresponds to node 1. I will have expected that if I substitute x equals 0 here, that I get a quantity of 1. Let's see if that's true. Can I plug this in here? X equals 0, 0, I get 1. Yeah. I have Kronecker delta property there. Okay. Likewise, when I evaluate what is this quantity at x equals L at the other side, at the other node, you will see very quickly that if I put L and L here, I get minus 3 plus 2 is minus 1. So I get 1 minus 1, 0. Okay? So it satisfies the Kronecker delta property. And I can also check what for N2, N3, and N4. Okay? You can check them also. And it's going to work out. It's going to satisfy the Kronecker delta property. Okay? Now, I'll move on here. Now, one thing to point out, you can, for N2, I cannot just substitute 0 here. Because N2 goes with the rotation. And so if I put 0 here, that doesn't make any sense. I'll get 0 actually. What you have to do to verify this one is take the derivative of N2. Let's take the derivative of N2. What do I get? I get 1 minus 4x divided by L plus 3x squared divided by L squared. If I now substitute 0, I get this 0 and I get 1. Okay? It works out. And you can check that at M prime, at the other node location, L, you will get 0. So you can check all these things. And you can plot them. You can plot these things, these shape functions. This is how the plot looks like for N1, N2, N3, and N4. And here, what I've done is shown you the value of the shape function, of each of the shape functions, at x equals 0 and x equals L. Okay? And those are the values. These for the first one, second one, third one, and fourth one. There's a question in the back.
Just wondering, these shape functions have to be the requirement of having a complete polynomial like basis functions have to?
Yeah, they're complete. They're linearly independent. And they satisfy the Kronecker delta property as shown here. Do you have a question?
So I'm wondering why would N1 be complete?
N1 is what?
Wouldn't N1 not be complete? Wouldn't it be missing an x?
Well, remember when, okay, so the question for the video is why is N1 complete? The answer to your question is in the homework, in the exam maybe, there are problems where you have to satisfy the essential boundary condition. You're forced to do that. And when you do that, some terms will not have shown up, right? But as long as you satisfy the essential boundary condition, that's what it matters. It is complete. In fact, it is complete, and I know that because we started with a full polynomial. I started with a full polynomial here. You see, I started with a full polynomial here. I didn't skip any terms. So it's complete. And I tried to enforce that by satisfying all the boundary conditions, and I came up with my 4 basis functions. So by doing that, it guarantees me that what I have is robust, complete, satisfy Kronecker delta property, satisfy partition unity. Now, this is a more systematic approach. In weak form Galerkin, it was not very systematic. It was like, you figure it out. You tell me how the polynomial looks like, remember? You have to come up with that first term first, and then figure out what your second term looks like, and your third term. I didn't tell you how to figure that out. You have to figure it out on your own. Here, I'm basically it's systematic. I'm kind of stuck. I know what my shape functions, basis functions are going to look like. And I know that it's going to meet certain properties, and I can check it whether it's correct or not. Okay? So it does work very nicely. All right, so you can also go home, actually, take W tilde and plug in all these N1, N2, N3, N4, and check that if I set W tilde at 0, I get 0. Okay? It will satisfy all of them. It's going to give you, sorry, at W tilde at 0, you should get V1, I'm sorry. And you will get that. You will get it. So it's going to satisfy all these boundary conditions for that element. It's going to work out. Okay, so what is my next step in developing the solution, the element formulation? What is my next step? Now I have my approximate function. I have my approximate function here what do I do now? What is my next step? I plug it into weak form. That's what I do. For W, I select the approximation function. For the weight function, what do I select? Each of the basis function, okay? Each of the basis function. How many equations will I have then if I select each of the basis functions for V? I will have 4 equations. How many unknowns I have? 4. So I will have a 4 by 4 matrix, hopefully, when we get through this. And in preparation to doing that, I realized I have a double prime, right? To prepare for that ahead of time, I calculated double prime here, which is basically derivatives of shape functions, double derivatives. And I'll call this B. I'll store it in my memory. That's B bold, and then this is my deflection vector, D, okay? And you can calculate B very quickly. So B's, if I know the N's, can I calculate B's? I mean, so these are these guys here, okay? I really encourage you, when I derive these things at home, which I actually did at home, and I also typed it, I think you also should derive it at home, because that's the only way you will learn. I mean, I'm sorry, some of you will probably pick it up and remember forever, but for others, I think it's important you actually write it out. For me, I had to write it out when I took the course. You know, I couldn't, the professor or the teacher will say, this is true, and I say, yeah. I had to go home and check it, okay? I encourage you to do it also. All right, so now I'm prepared. Now I'm prepared. I have double prime for that. I have a single, I think I have just a V there, so nothing more here, really. So I'll plug it in for each of the equations. I did it here. For each V, so for V I put N1, so you can see there, the N1s. For the second V I put N2. For the third equation put N3. You can see it here very quickly. And you quickly realize that for the first equation as an example, let's do the first equation. For the first equation, do you realize that it belongs to N1? You realize that this is 1 here. It is 1. And then you'll also notice that these will be zeros. These guys will be zeros. Okay, so you have 1 there. And then for the second equation, you'll find that this is 1, but the rest are 0. For the third equation, you will find that all these other ones are 0 except for that one. That will be 1. And then so forth. Okay? So in reality, you get, if I look at the 4 equations, what I got for the boundary condition is Q1, Q2, Q3, Q4. May as well just put in a matrix vector Q bold, right? And then also you notice as N1 double prime, triple, N3 double prime, N4 double prime. This is basically B, but transposed, doesn't it? Let's look back here for a second and notice that. So it's basically B, but transposed. You agree? Everybody agrees? Yes? Okay. So when I do that, I get B transpose. I'll put it on the left. And why do I know that I should put it on the left? At the end, I should have a 4 by 4 matrix. If I had done, by mistake, B times B transpose, it would be wrong because B is 1 by 4, B transpose is 4 by 1, so I'll get a 1 by 1. That's not right. I should get a 4 by 4. So you know that the B transpose should go on the left. You also notice this N1, N2, N3, N4 are in a column. So that's basically N transpose. You agree? I defined that earlier, if you recall. That's basically it. That's my element formulation for beam, right there. And the D does not depend on dx, so I'll bring it outside. And this is my stiffness matrix right here. And this is my force vector. This is due to distributed forces, and this is due to concentrated forces, or internal. These are internal loads, by the way, at this point in time. There's a question.
If this was several elements, so that vector Q would be only on the elements that we have applied the order displacement?
So the question is, if I have that Q for several elements, remember the Q is only specified at the very end of the problem, once you assemble everything together. This Q here. Remember, these are internal quantities. Okay, we'll give some examples so you can see how this works. Okay, so now another way to do this, another exciting way maybe for some of you, or boring for others, if I minimize this total potential energy, if you remember this, we derived this formula before. If I minimize this, I get the weak form. If I start from here, the strong form, and I develop the weak form, I get that. So they're all three connected very nicely. So I could probably start here too. I can start there and do the same process and see if I get the same thing. And I did that. This is the total potential energy, and I plugged in. I did a trick, and this is a trick I've been doing for a little while now. You see me do it. W prime, I separate into two of them, and this one I put transpose. Oh, this is a scalar quantity at this point. It's not a matrix. But W prime transpose times W prime, really, the scalar, the transpose of a scalar is a scalar. So this times that is really that squared. Here I didn't do anything. That's fine. And here is really quick. What do you have to do? For W prime, you put BD, right? Remember W prime was BD? Let me remind you, I see some faces of confusion. Look at this, B. D is W prime, just to remind you. That's where we were at. And don't feel bad, because I've been doing this for a long time, and even when I'm doing this at home, deriving it, I have to look back and check. Remember, trust the system. Trust that what you wrote before is right. Okay, except if you're doing a midterm, you have to check your work 10 times, right? Okay. All right, so we plug this in. For W prime, we plug in BD. For W prime, we plug BD. Okay? And then for W, plug in D transpose N transpose. And for these guys, we plug in D transpose Q. It's basically D transpose Q. And now I realize here that this order changes, because when you have a matrix times a matrix of the transpose, basically the order changes. So I have D transpose first, B transpose next, and I have B, D, D transpose, N transpose, just like that. Okay. Now I take, if you remember from maybe 2 lectures ago, we already covered this. If you minimize the total potential energy with respect to V1, theta 1, V2, theta 2, in reality, all you're doing is just remove this D transpose here, this D transpose, this D transpose, and you're left with the equation for the element. This equation here matches what I got with weak form Galerkin. It gives me the same thing, exact same thing. Okay, so I'm showing you many different examples I've given now where I use total potential energy and I use the weak form. In both ways, I got a really nice answer. Okay. All right. So any questions on that? Okay. All right. So now that I have this done, why not just plug in this into Mathematica? I know B already, B transpose, I know B. Plug it in, just Mathematica do the integrals for you. And you can basically get the answer to the problem. So the stiffness matrix for a single element, local stiffness matrix, the element stiffness matrix looks like this. It's 4 by 4, and you have V1, theta 1, V2, theta 2. And then this is your distributed force vector, okay? And then you have the internal loads, Q1, remember this, Q1, Q2, Q3, and Q4 are internal loads to the element. And so here are your vector for that. So now you're ready. Now you're ready to solve any problem that you want to do. But now you have to, the next step, I have the element formulation for one element. Then I have to, basically, if I have a, this is what you will program into Abaqus, say. If I was the Abaqus programmer, the one developing Abaqus, this is what I'll program in. And then, from now on, if I give you a problem, you'll discretize it yourself. You will calculate this for each element, right? And then you'll assemble it. And then you'll solve the system of linear equations. Linear in this case, okay? Any questions? Okay. Okay. In the connectivity, the code number, you're going to start here 1, 2, and then 3, 4. So when you write it here, it'll be 1, 2, 3, 4, 1, 2, 3, 4. Okay. Okay, great. So that for a uniform load, for a distributed uniform load, transverse load, for that special case, you get QL over 12, 6 minus L, 6L. Let's see if this is correct, whether this makes sense or not. QL over 12 times 6 is how much? QL over 2. QL over 12 times 6 is QL over 2. That goes with that node. This goes with that node. That makes sense. That's the transverse load that has to support that load. So what is the distributed load? Uniform load? Q, right? What is the length? L. Q times L is the total force acting downwards. So it has to be supported by QL over 2 here and QL over 2 here. It came automatically. Okay. We can also discuss the moment, although it takes a little more work. So let's skip that here for now. Okay, any questions so far? I just did a special case, but this is the most general case for Euler Bernoulli beam. Okay, so let's do an example. I think an example is a great way to illustrate this. I have this beam. I have a boundary condition here, a boundary condition here. I put a couple here and a force downward force here. Now, I don't know if you remember this, but maybe mechanics and materials. Don't solve like a differential equation for each piece and make it equal to each other and then solve like a bunch of differential equations and all that. Well, this method is seamless. It just works for indeterminate systems, for determinate systems. I don't know if you remember also in mechanics and materials there was a case where the system was indeterminate, so you will put a fake load or you'll remove the boundary, right? Some people in the back are saying yes. I assume that you guys all took mechanics and materials, right? Do you guys work with indeterminate systems? Right? So if I have a clamp condition and a pin condition here, and I put a distributed force, there's a lot of work there to do because you have to figure out how to deal with indeterminate problem. You don't have to worry about this anymore because we can use finite elements. And so here, I'll divide the domain into 3 logical elements. I could divide into 200 if I want. I just did 3. One here that stops there and coincides with that. A second one here that stops there and coincides with that. So then I have 3 elements. And then these basically V1, theta 1, V2, theta 2, V3, theta 3, V4, theta 4. Basically, this is what I have for my system. Now, if I were to write the code numbers, the connectivity matrix, for element 1, I have V1, theta 1, V2, theta 2. For element 2, I have V2, theta 2, V3, theta 3. For element 3, I have V3, theta 3, and V4, theta 4. I can now very quickly apply for element 1. I'm showing you how to write the code basically. If you were to do this in MATLAB or some code, I already expanded it. I already know that I'm going to have how many unknowns?
8.
I have 8 basically. So I just create an 8 by 8 matrix, big one, okay? And I populated element 1. So element 1 goes here, okay? I populated there. For element 2, it's somewhere here, okay? Okay, and you can check it that I put it in the right location. Makes sense because it has the 3rd, 4th, 5th, and 6th position. And if I look here back, 1, 2, 3, 4, 5, 6. I'm in element 2, so that's 3, 4, 5, 6. So it has to encompass that block from 3 to 6. And so if you see here, that's what I did. I'm populating the block that's 3 to 6. 3, columns 3 to 6, and then row 3 to 6. I'm populating just that. Okay, and then I can now populate element for element 3 here at the top. So here the bottom 4 blocks basically 4 through 8. Okay, all filled out. Now I can assemble it together. I'm doing it differently than I've done it before, but I'm going to maybe teach you how to code this up. So I'm showing you big picture how the code is working. Okay, so now I can add element 1, 2, and 3 together, and then these are the assembly ones. This is how you get automatic assembly there. We can do it old school, like I taught you before. We can put numbers for each row and column, right? Remember? 1 through 4, and then assemble it the old way. That works too. So now I have my 8 by 8 matrix. I have my unknown quantities here, and then I have the external loads now. These are the external loads now, because the internal loads from one element to another add up to form and to basically be equal to the external load. So now I'll impose the boundary condition. That's the next step. So when I impose the boundary condition, I know on the left-hand side, remember it was clamped? Yes?
Yes.
So if it's clamped, then V and theta are 0. Then, I don't know if you recall, but in that next node, I had a pin condition. Is everybody with me here?
Yes.
So then that's 0. And if you recall, the next node over, also I had it fixed vertically, remember? So I imposed those boundary conditions. And on the left-hand side, because these are imposed, these must be reaction forces. They have to be. And if you recall, in node 2, did I apply any moment? I didn't apply anything. Let me show you the picture in case you can't remember it. That was a picture. That's node 1, node 2, node 3, node 4. There's nothing here. I'm not applying any moment there. But I am applying a moment there. So when I look here, V3, node 3, I'm putting a pin condition. So I must have a reaction force. And then I'm applying also a moment in that location of minus C, the opposite sign from what I have developed for general element. It's in the opposite way. So minus C. And then in the end, remember at the end of that, I apply a force downwards, minus F. Did I apply any moment at the end? No, so that's 0. And so now, okay, this may look messy here, but it's not that messy. What I did is I try to cross out anything that has zeros. And then if you look here, you're left with solving this, basically what's left. Okay, you can just solve that. Okay. Here on the left-hand side, I reduce the stiffness matrix. These are the only ones that are non-zero. The only ones that are non-zero. You can solve here for the deflections, theta 2, theta 3, V4, and theta 4. And once you have this, you can get the reaction forces by plugging in these numbers. Okay. All right. How many follow that example? Do you follow that example? Excellent. Thanks for raising your hand if you did or nodded. That's very helpful. Okay. So let's look at another example. Another example here is a distributed force that's acting part of the beam, A, and for the rest I apply a downward force, F. In this example, I will divide into two logical elements, one here and one here. And here you can see how I set it up, okay? So the next step is discretize the domain into elements. Element 1, element 2, and then I have nodes 1, 2, and 3, okay? For element 1, I just use the formula. That element formulation that I have is I can use for any element. I just have to change the length. The length is A for the first element. The length is B for the second element. Okay. So I did it on equal element size, so you can see that this element can be used for either longer or shorter, or doesn't matter what. And so if I do that, oh, by the way, how many degrees of freedom I have here at the bottom? 6. So that's why I have a 6 by 6 matrix. So I expanded it 6 by 6. Oh, my force vector. This is my force vector. I used the, remember I had the special case for uniform loading? I just used that formula here. And then these are the internal loads acting on that element 1. Then for element 2, again, this occupies the bottom right block. And basically I'm ready to assemble. I'm ready to assemble now. The global assembly is this one here, okay? The internal loads add up, and they have to be equal to the external load applied. In this example, remember the left-hand side was clamped? So U1 and U2 is 0. That's it. On the force side, oh, these are 0, I must have a reaction force, don't I? So I put Q1 and Q2 there. And also, at U3, I had no force applied. At U4, I had no moment applied. At U5, I had no displacement. I had no moment applied. I think this is probably wrong. Okay, I applied a force downwards. That goes with V3. So that's a small error here. F should have gone here and 0 at the bottom. There's no moment applied. So switch F and then 0 here. It was a small mistake. If you can help me record that. Excellent. Now I'm ready to solve the problem. You can just solve the bottom 4 equations, basically. 4 unknowns, 4 equations. Solve for these 4. Once you have it, plug it back in. Multiply the stiffness matrix by this column, and you will get the reaction forces Q1 and Q2. Any questions on that? Simple? Yes? Probably the simplest class so far, maybe. I don't know. Or maybe you're getting used to the idea of facing these differential equations with Wick from Galerkin, Riley-Ritz, and so forth. Okay, so how do I do this with axial flexibility? What if I have axial flexibility? Not only have transverse loading, but I also have axial loading to that bar. I can do that. I can do that. All I have to do is the principle of superposition. I already divided the equation for a bar. I know the equation for a beam. So now, instead of having just V1, theta 1, V2, theta 2, I'll just add here U1 and U2. You follow? Yeah? Yeah, because V1 and theta 1 and V2, theta 2 are acting vertical. Theta 1 and theta 2 are the rotations at each end, the slopes. And then U1 and U2 are the axial displacements. Why not just combine the two? And then I have a nice element that does axial loading and it does bending. You see my point? Okay. If I do that, then all I have to do, I already know the stiffness matrix. Remember the stiffness matrix for elastic bar? What is it? You should know this by memory now. I've done it like 5 different ways. EA over L, 1 minus 1 minus 1, 1. Remember? Yes? Okay, so all I did here is augmented the matrix, and now I have EA over L, and you see zeros everywhere else because I don't want to couple this deflection here with a vertical load. This deflection is what causes the beam to stretch, and V is what causes the beam to bend. I don't want those to get coupled. So that's why you see those zeros there. And I should have a minus sign there, symmetric, and then I have that. Okay? I'll let you stir for a few minutes here. Yes? Fairly simple, right? All I did was to augment the matrix to include the axial flexibility. Okay?
So there's no coupling between beam and bar?
In this theory, there's no coupling between vertical displacement and axial displacement. In this theory, I can make it coupled if you want for your final. I can make it into composite material. A composite material, if you have an asymmetric composite material, right, then you can have coupling between stretching and bending. Okay?
As long as it's isotropic, it's not coupled.
In this case, fully isotropic. So in this case, there's no coupling. But we can make it very coupled, very quick. Okay? All right. Any questions? A simple example. Take two metals, one very weak and one very strong. What do you think will happen when I stretch that bimaterial part? It should have some bending because it's not purely symmetric, right? There's some difference in there. Okay? Yeah? In modulus, there's a difference, right? And thickness. So maybe I'll get some bending. Okay? But in this case, we're assuming everything is isotropic. Okay, I'll let you stir this enough. All I've done here is combine the matrix I developed for beam with the matrix that I derived for elastic bar. That's all I have done. I'll complicate it a little bit more because I need to. This is too boring otherwise. What if I want to take that beam and rotate at some angle? Why not do that? What use does it do if everything was straight? I can't solve a single problem, I don't think. Maybe I can solve the few problems, but not a lot of problems, right? Like the one I showed you at the beginning of the class with these bridges and this tower, right? Truss tower. Can't solve that. I have to be able to rotate it also. So if I rotate it amount phi, I won't go over this 100% because I kind of covered how to do this before with the trusses. But it's the same process. Here what I'm doing, you can see here u1 prime, v1 prime, and I have u1 and v1. And then I have u2 and v2, and then u2 prime, v2 prime. So I'll develop the elements in the prime system. In the prime system, you agree that in the prime system, the local system, I know what it looks like, the stiffness matrix, I know exactly how it looks like. I showed it to you. It was this one here. This is true in a local system. And I can rotate it around, take it with me, as long as that axis along the length stays along the axis for locally, this is true. But I have to relate it to the global system. I have to relate it to the global system. And to do that, you have to transform it. You have to transform it with this transformation matrix. And notice that on the third row and third column I have a 1, and the third row and third column I have a 1. I have a 1 there because rotations, if I rotate it, the slope doesn't matter. The angle is theta, doesn't matter what coordinate system. So it's not affecting that. The only thing it's affecting is u1 and v1 and then u2 and v2. For that reason, the transformation matrix we use for trusses is basically identical, except for this extra 1 here that's for the rotation. So if I multiply this transformation matrix times d, I get the local system. Okay? This particular t, if I multiply by the global, this u2, v2, u1, v1, I'll get the local system d prime. Okay? And then this is your d right here. Now I can do the same with the forces. For the forces, the same way. P1 prime, v1 prime, p2 prime, v2 prime. The moment, the same way, the moment doesn't really transform because the moment is a moment. Doesn't care what coordinate system. That's why you see a 1 there for that. And then 1 for that one. Okay. Similarly, I can take the force in the global system times this transformation matrix gives me f prime. So this is a transfer function. This is a transfer function between the global coordinate system and the local coordinate system. And it's the local coordinate system for which I know the stiffness matrix. That's the one I know the information about. Okay. All right. I can also, if I had a distributed load here, in a local system, I can also convert that to a global system. So here, for example, f prime could have distributed forces also. You could have that situation. Okay. Okay. Any questions? Any questions? The shape functions. N1, N2, N3, N4 are the shape functions for a beam. I added, remember, this row corresponds to the axial, so that's why there's a 0. And this row here corresponds to axial loading also. So the distributed load is acting perpendicular to the bar, the beam, right? Yes? That's why you don't see anything here. Okay? You get it? Yes? We're good? Okay, so now I'll use these relationships. I know that f prime equals tf. I know d prime equals td. I also know that f prime equals k prime d prime. And this k prime, I know it. This k prime is the one I gave you earlier, this big one here. Okay? So all I have to do is for f prime, I substitute tf. You can see it there. For d prime, I substitute td. That's there. I want to solve for f. So if I invert t, I get t inverse. Now t inverse is t transpose, remember? Yes, remember from trusses? Yeah. So then you get f equals t transpose times k prime times t transformation, t. So this becomes your new stiffness matrix. And f and d are now in a global system. They're now in a global system. Okay? Yes? So fairly straightforward, I think. If you've done trusses now, you should be able to do this one as well. Okay. So here's some examples where you could get beams with axial flexibility. So this is not made up. These are situations that could happen. Say I have a frame and I apply a force here and a force here. I could get some amount of bending. In this case, I have a hinge here and a hinge here. If I apply a load this way, these guys are acting like pins. Can you see that? Like if I have a beam on a roller, can you see that? And then can you see that these guys here can act like a spring, preventing the bending? Okay. So all I'm trying to point out with this picture is that these situations are real. They can happen. You can have beam and axial loading at the same time. Let's not spend too much time on this, because I want to show you that Abaqus has its elements. In fact, if you did this by hand, you'll get the same answer as Abaqus. Okay? What we're trying to do here in this class, we're trying to give you the fundamentals about what the code is doing, Abaqus is doing, but we also want to give you some practical experience. And sometimes it's very difficult to know if you just use the Feynman code and you don't have any theory knowledge of what Abaqus is doing, or Nastran or ANSYS, it's difficult to know what to look for sometimes. And so now you guys know Euler Bernoulli beam, right? Can you state that? Do you feel good about that? I feel good. I think you guys get it. So knowing that information, when you read the theory manual for Abaqus, this came from the theory manual of Abaqus. You can see here, oh, B is for beam. That's the element type. Okay, 3, that's whether I have a beam in the plane or 3D. Well, everything I analyzed today was in a plane, right? You agree? So it's probably 2, what I'm going to select for the examples. 1, okay, so 1, linear, quadratic, or cubic? Huh, that looks familiar. I guess linear is linear interpolation, maybe? Is that sounding familiar? Or quadratic interpolation, or cubic interpolation? Well, I think it's cubic, remember? That's what we use, cubic. So that, most likely the example we'll do is 2, 3, okay? And I won't discuss this other one. These are other options you have. Okay, so B23 is the element we actually derived in class today. This is the one we did today. I won't do B33 because that's 3D and it's more work, right? But you guys, as long as you get the idea of what we're trying to accomplish, I think, you know, if you read the theory manual on how to derive this element, you'll follow it at this point in time. They have a theory manual that's very strong. So now let's read. This comes straight from the theory manual. Let's read to see if you guys understand what this is. Euler beam, slender beams. Is that what we talked about? The Euler Bernoulli beam is good for slender beams. I continue reading here. Euler Bernoulli beam is available in Abaqus standard. Fine. These elements do not allow for transverse shear deformation. Isn't that what we said? That the cross-section remains normal after deformation, so the transverse shear is 0? Yeah? So you understand what we're doing here then in this class. We're giving you a theory, and so now I go to the manual, I know what they're saying. I know exactly what they're saying. Plane sections initially normal to the beam's axis remain plane. I just said that, didn't I? And normal to the beam axis. They should be only used to model slender beams. We talked about that. The beam's cross-section dimension should be small compared to the typical distances along its axis. The only difference between what they wrote and what I say is they probably said it better than I did. Okay? But I think I said the same thing. For beams made of uniform material, typical dimensions in cross-section should be less than about 1/15 of typical axial distance. For, I don't know, it got cut off, okay? Let's read the bottom here, interpolation. This is continuous, so I did a print screen interpolation. The Euler Bernoulli beam element uses cubic interpolation. Didn't we just derive it? Okay? Which makes them reasonably accurate for cases involving distributed loading along the beam. Blah, 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 blah. Okay? The other parts you may not understand because we haven't gotten to that for dynamics. But if we get to that, you will see that as well. Okay? Are you seeing now that what we're discussing is not out of the blue? Okay? It's connected. Okay? It's connected. And the trusses. We did the same with trusses. I didn't do a print screen of the Abaqus manual for trusses, but it's the same way. Okay? Now when I go here and I do an example, so I have, I selected, basically this is the original, I basically took a beam here. That's another beam here. Okay, so 2 beams. I apply a load in this direction. Okay? And it deforms to this point. So it deforms to this point and it looks like that. Okay? So that's an example like this. This is a deformed case. That's an undeformed. Sorry, this is in correct. This is incorrect. This is an undeformed. That's a deformed. So I made an error here. Okay, I labeled incorrectly. In this example, beam square cross-section is 1 inch squared, elastic modulus is 10 MSI, applied load of 9,000 pounds. So how do I do that? So I have only 3 nodes to worry about in this example. 1, 2, and 3. Okay. I put some nodal coordinates. Element type equals B23. 2 is planar, 3 is Euler Bernoulli cubic interpolation. So then I have 2 elements only for this example, 1 and 2. Okay. Beam section, so I have to define the section of that beam. I have to tell it, what kind of beam section do I have? Do I have a circle, a square? What do I have? So it's a beam section. I said section equals rectangular. Now, how do I know what options do I have? So Abaqus has something called the keyword manual. Okay. And the keyword manual will tell you what options you can select. You can select a square with a thin wall, or a circle, a hollow cylinder, a pipe, for example. You can select many different cases. You can select different inertias. If you know the cross-section of the beam, and you don't know the geometry, but you know the inertias, IXX, IYY, IZZ, all this, you can define that directly also. The element set is LM, material is aluminum. So then I say, okay, material name equals aluminum, elastic, modulus 10 MSI, plus notation 0.33. I'm going to fix, it's clamped here at these nodes, 2 and 3. I made them into an element set fixed. I put the 2 nodes there, 2 and 3, right there. I put them in a set. On the side I'm applying the load, I put a set name just to keep track of the name, load application, I called it. That's for this node here. And then that's it. Step, static, boundary, fixed 1 through 6. C load, concentrated load basically. And then load application in the one direction, 9,000 pounds, end step. Run, bam, done, given here. Okay. And then if I want to check the reaction force, just for the kicks, I was checking to see if I did it correctly. Which I'm kind of teaching you how I check my models. So I know I applied 9,000 pounds. Well, this should be reacting 4,500 pounds. And that's what I got, 4,500 pounds at these nodes. I checked other things like displacements and, you can check many things. Okay, you guys follow this example? I also did a check also, just for fun. Just one element, but put a plane of symmetry. Can you see that there's symmetric about here? So I made it symmetric, and I allowed this to move in this direction, with a roller. And I fixed the rotation so it didn't rotate. Okay, so doing that, I got the same answer. This one moved 0.183. This one moved 0.183, just with a single element. You can see here, just with one element, I did it. And then the boundary conditions look different now. Because for the load application now, I'm preventing it from moving down at that location where I'm applying load because it's symmetric. I'm not letting it go down. And also I'm not letting it rotate at that plane because you can't rotate about that plane. And with that information, I also put half the load, so 4,500 pounds because I'm only simulating half of it. Okay. Got the same answer. Okay. Okay. All right, so I was thinking that it would be a good idea now to try our experiment again, where we're going to try to teach Abaqus using interactive, in this course. So with that, let's take a couple of minutes break. Next Tuesday, I'll cover Timoshenko beam theory, which is also used in Abaqus. So Timoshenko is in Abaqus. That'll be the next lecture on Tuesday, okay? For now, let's try this experiment again and see how we can do this.
Okay, so to use the application in Abaqus, we're going to solve this problem. It's a plate with a hole in the middle under uniaxial stress. All right? We're going to take advantage of the 2 planes of symmetry that we have in this problem. So it means that we're going to just model a quarter of the plate. Okay? If you remember the stress applied, the remote stress, is 100 megapascals. We're going to distribute this stress across the thickness by multiplying to the thickness. So it means that the load applied through the model in Abaqus is going to be 1,000 kilonewtons per meter. So let's switch to Abaqus. And let's start with the first part, the first section, which is basically the CAD of the problem. In order to do that, we need to go through the toolbox area. We need to click and create a part. Once we create a part, we can name this part by plate, for example. This is a modeling in the 3D space. The type is gonna be deformable. And for the shape, we're gonna use shell. It could be also possible to solve this problem by the shape solid. But we can simplify it by using a shell shape. The type is going to be planar. So this is basically the characteristics we need to set up. The approximate size for this grid, due to the geometry of the problem, is going to be 2 at this moment. And you just continue. So we can use all the icons we have in the CAD. So let's draw a rectangle defined by 2 vertices. So let's pick the first vertex and then select the next vertex. Our dimensions for this rectangle, which is, I remember, is a quarter of the plate, is going to be 1 inch by 1 meter, sorry, by by a half a meter. So if we go to this icon, we can define the dimensions for the plate. So just click in the side of our interest, remove, click again. We can go to the prompt area, which is right here, and we can type 1, enter, and you can see that the dimension is modified. If we repeat the same procedure for the other side, we can obtain the desired rectangle. All right. What's the next step? The next step is to model the quarter of a circle that belongs to the quarter of the hole in the plate. So let's go to this icon, create an arc based on the center and 2 points. Click on that, select the center, which is this. Click in the first point for the arc, which is the intersection with the plate, with the rectangle. Just click there, and then drag to the next point, which is the next intersection. When it is done, just click Escape, and let's define the radius for the arc. So let's again to this icon at dimension, click in the arc, drag to the center of the arc, right, and define the dimension. In this case, it's 0.02 meters, the radius for the hole. Just enter. This is the new hole. If you want to fit out of fit all the CAD in the grid, you just need to click this button, out of fit, on top, and you will be able to see it. So once the CAD is done, we need to finish this section just by click done in the prompt area, and the part will be done, will be created. Let me see. Give me one moment. Oh, I missed one part, sorry. You can see that we have these small segments that we need to trim. I forgot to do that. So let's go to trim, which is this icon, auto trim, and pick the segments we need to remove from the CAD. Now it's done. should work. So now push down again, and here is the part. All right. So let's move to the next module in the yes.
I have a question. When you trimmed it, it became a solid part automatically, or do you have to click something to make it a shell?
No. Once I push down, it becomes a solid part automatically.
It knows that it's now a solid part.
Yes, it's assigned as a solid part. Yes.
Where do we define the thickness? Did you already do that?
We're going to do it later. Okay, so for now we have the cat, which is basically a rectangle. It's a plane. Okay. Now let's move on, and we're going to define in the toolbox area. We're going to define the material first. The material is going to be steel for this case. Since this is an elastic problem we are solving, so let's push mechanical, elasticity, this is the problem, and elastic. All right, so the new window, we need to specify the type of material we are modeling. So this is an isotropic, so by default it's isotropic, we should change this condition. But we need to define the Young's modulus and the Poisson ratio, okay? Remember, even though we draw a plane, this is a solid model. So it would deform in all directions. So we need to define the Poisson ratio in order to take in account this effect. So for the steel, we have 200 gigapascals, and the Poisson ratio we're going to set as a 0.3. Let's push OK again, and the material is created. You can verify it by clicking the icon to the right, which is the material manager. You can check that the steel material has been created. Now, probably this step is going to answer your question about when we need to set up the thickness for this model. So we're going to create a section. That section, let's call shell. That's going to be, the category is shell, right? And it's homogeneous. So this is, the previous step was the cat. Now we are getting to the final element model by itself. So if we continue, this window that pop up allow us to define the thickness for the shell. So in this case, the thickness is 0.01 meters. Okay? Check that the material is the one we desire, that is steel. And we can use any of these two numerical methods of integration to carry out the integrations, as we did. So let's check Gauss, just to match what we already done during the class. And if you remember, for the Gauss quadrature, we need to define the number of points of integration, right? We learned that 2 is most of the time the number of points of integration that we use. Okay, let's do 2. However, later on, I'm going to use another feature when I will require a reduced integration. So I would prefer to stick with 3 as is stated in this window as a default, because I ran it with 2 points of integration, and the results were more accurate with this number of points of integration. So I'm going to stick with 3 for now. So let's push OK again. And now what is left is just to assign that section, that shell section we created, assign to the cat. So both with match, right? So let's go to the assign section. We can create a set or not create. It's not relevant at this moment, just uncheck. Let's minimize the model. Okay, it's selected. let me check that it's correct. I don't know, it's not working my drag today. Okay, it's selected. So just push done. That window is just to verify what section we are assigning to this CAD model. So it's the shell section. We don't have another option. And here you can see much better in this area what is the shell mean. Even though this you can think it's a membrane, but it's not a membrane because it's a solid, so we can define this more like a plate. Okay? So if you click in definition, we have a top surface, we have a bottom surface, right? So it's still a solid. So we are going to base all our calculations in the middle surface, like we used to do for the plate theory. So this is like a plate in this case. So it's done. What is the next step? The next step is create an instance. When we are creating an instance, it's basically right now we are getting to the FEA final element model. So we need to create an instance for that purpose. It's like bringing from the CAD something to the final element model so we can apply all the conditions. So by default, is they create an instance from a part. We're going to stick with that. We're going to say that it's dependent because it's my interest to mesh on the part instead of the instance. So let's keep it as dependent and push OK. The instance is created. What is next? Let's apply this create that step to later on apply the load. So let's name, if we go, let me get back. If we go to this icon in the toolbox area, create a step, you click on that, you can name the step, let's say load. This step is going to be created after the first step that is initial, so just for information. And the type of step, the procedure for the type is a static general. This is what we know, because this is the kind of problem we are solving. Continue. Since this is a static, we are not defining, for example, for the nonlinear cases, we need several steps to apply the load. This is just one step, one load, right? So we don't need to modify any condition, any setup here, because it's only one step. So just push OK, and the step is created. You can check in the step manager that we have two steps, the initial step and the one we created to apply the load. So let's move on and apply the boundary conditions to this problem. So let's start with the essential boundary conditions. So, OK, let me get back. By clicking in this icon, we can create the essential boundary conditions. So the essential boundary condition for this problem, let's say this is the left side for the plane number 1. We need to set up the step as initial. We need to select in category mechanical. And in the type of selected step, we're going to state displacement. All right? Could be symmetry, but it's much better displacement in this case. Continue. We need to select the left side edge. Done in the click done in the problem area, and apply the constraint in this area. So this side is not allowed to display better. It's only allowed to display in the U2 direction, in the 2 direction. So let's click the other options. OK. Let's do the same procedure for the bottom side, which is the one that is lighting up in orange. Let's repeat the same procedure. Bottom side 1, initial, mechanical, displacements, continue. Exactly the same step. This time we pick this edge at the bottom of the plate, click done, and the only possible, the no constraint displacement is going to be in the one direction. By doing this, we are replicating or applying the symmetry of the problem, okay? Basically, just as an example, this line cannot penetrate the quarter of the plate that is below the, right? This is basically what we're doing, is making a physical sense of this. So what is left is just to apply the load. So let's click in this icon, create load. Let's name as a load. Now, for the load, we need to apply select the step we previously created, that's load. The category is mechanical, and we're going to use as a type for the selected step the shell edge load. So basically, it's a distributed load over a surface. It's not over a line, it's over a surface. So this is what we want to do. So shell edge load, continue. We select the side of our interest, which is this right-hand side edge. Click done in the prompt area, and we just need to define is the magnitude for the load. Remember that we made the distributed load across the thickness. So in this case, that load is 1,000 kilonewtons, which is basically 1 e to the 6 newtons per meter. Okay? Yeah. We don't need to modify anything else in this window. Just push OK, and oh, I did something wrong. You can see the load is going in the opposite direction. Okay, so let me get back and re-edit this load. So that makes sense. Let's go to the load manager, which is the icon to the right. Click on that, edit, and just change the sign to match our problem. Push OK. We can close this window, and now you can see that our load makes totally sense. All right, so what is next? Let me do something. The next step is mesh this part. So I want to compare. I'm going to just duplicate this plate. I'm going to do that, and in order to compare the mesh between one to the other. So the steps are going to be basically the same, except for the next step, which is the replication, the duplication of the plate. In order to do that, let's go to the module 3. In the module 3, locate where the parts icon is. Expand the parts icon. Right-click in the part that we created under plate. Just right-click. Okay. I have some problem. Okay, let me try to do it here. Let's go to the top part, copy, plate. Okay, we rename, name the copy. Let's put it plate 2. Okay, and just OK. Now we have two parts. How can you verify that? If you go to this section, you can check that you have plate and plate 2. We have two parts. They share some similar characteristics, like the features. It's a shell planar, and the section is a shell homogeneous. How did you do that? Just by expanding next to the name for the plate. So the plate is fine. But we also need to create an instance for this plate. So in order to do that, we can do it here in the module 3. Look for assembly at the bottom. Okay. It's not working my right click in my mouse. So this is what I'm going to do. I'm going to go to the top. Yeah, thank you. Thanks. Okay, just give me 1 second. All right. Okay, so let's get back. Right click. Thank you. And all right. So this is what we want to do. We want to create over this part a new instance. So let's go to assembly. Here. Okay, let me see if I can figure out what I'm doing. In the assembly, we need to create an instance. Okay, I did it. So we need to get back to the assembly, click on instance again, and select the part of our interest. Okay? So this time is the plane number 2. It's dependent as well, and we're going to click this auto offset to be able to see both instances. So if we click this, we can see both instances. All right? Just okay. And now we have 2 plates with 2 instances. Now the next step is to this plate apply all the loads and boundary conditions. Yes?
When you created the copy, you put it next to each other. How does it know what distance away to put it?
What instance?
You put the next plate
Yes.
next to the one you have.
Yes.
How does it know
What
what distance to put it from the other plate?
No, it's you don't define the distance between that. It's set up automatically. You don't define that. So the left-hand side plate, it's the first one we created. The copy is the one to the right. Okay? Okay, so let's move on. Apply the same boundary conditions to this plate as we did previously. So go to load. In load, we're going to repeat exactly the same steps we did. So boundary condition, that's going to be left. Left side for the plate number 2. Step initial, mechanical, displacement, continue. What we need to do now is to select, let me do something here again. Left side 2, initial, mechanical, displacements, continue. Now we can select this line. Done. We click all the constraints. OK. Repeat the same for the bottom. Initial, mechanical, displacements, continue. Select this. Done. Let's constrain the plate. I don't want this. OK? So it looks good to me. Let's apply the load. We need to create a new load. Let's set load 2, step, load, mechanical, shell, edge, load. Exactly the same what we did earlier. Continue. Select the edge we need to apply the load. Click done. And then specify the magnitude for the load, which is 1 meganewtons per meter. All right. Now you can see both parts. What is next? Mesh. That's the interesting part. So we're going to mesh first the plate to the left. So we're going to see the part instance, which is basically set how many elements it's going to have. So this you need to be careful because we are using a dependent part to mesh the part, right? So we need to we need to switch to part in this area in order to do that, okay? In this moment, the part number 2, the second plate we created is the one that shows up. We want to select the first one, so just click, scroll down, plate, and now we are in business. Let's see the part. We're going to apply a global size of 0.02. That's basically the distance, the length of the element, or distance between nodes. If we apply, you can see those white dots around the plate. This is what we want. But we also want to specify, or specify no. We want to make more denser the nodes where the concentration of stresses happens. Okay. So in order to do that, we need to click in Set Edges. Let's magnify this. Click in the arc, click Done, and now we can specify the number of elements by size or by number of elements we want. Let's say for this plate by size, and the size for the element is going to be 0.01, even smaller than the global size we assign for all the edges. Okay? We don't need to specify anything else, just the size for the element. Click OK, and now you can see the new seat in this area. All right? What is the next step? The next step is go to the mesh controls and set what is the element shape. In the element shape, we're going to work with a quadrilateral. So this is going to be quad, and we're going to push a structure for our mesh. Pay attention to this scale of colors. When the part turns to pink, it means that the geometry of the part could allow us to conduct a free mesh. It's basically the program is going to do whatever they want. The geometry is completely arbitrary. You don't have any control about that. All right? However, if you want to pre-establish some specific topologies in the plate for your convenience, you can switch to a structure, and this is what we want. All right? We want quad structure for this case. So let's push OK. It turns to green, which matches with the scale, with the color scale. And then what we need to select is the assign element type. The assign element type is just by clicking this icon. In this window, we're going to select a standard because it's the correct. We have a standard and explicitly. I will take some more time to explain what is a standard. So just leave it like that for now and focus our attention in the geometric order, which basically is the order of our shape functions. In this case, it's linear. This is what we want for this model. So it's going to be a shape functions, a linear shape functions. Make sure that we pick shell here in the family of the element type, because this is the kind of element type we want. So we click on shell. We stick with the quadrilateral element, and we are going to apply a reduced integration. That's the Gauss quadrature numerical method that we use to integrate, right? So this is, you already know what is the reduced integration. We are lower 1 degree the integration. So let's keep with reduced integration. This is the element type we're going to use for this plate. S from shell, it was a surface, would be SF. Okay, let's click surface just for make the difference. You can see how it changed, right? So for shell, it's just S. 4 because this is a 4, it's an element defined by 4 nodes. And R because it relates, it mentioned reduced integration. So this is what we have. This is the element. Click OK. And what is left is just to mesh. So if we click in this icon mesh part, we just need to click to push yes. And the part would mesh. It looks like this. All right? Let's check how is the mesh at the whole. All right? Okay. Let's move on to the next, for the next part. So now we switch to the plate number 2. In the plate number 2, we are basically repeating the same procedure by assigning a global size of 0.02. Okay. We're gonna make denser the mesh in this at the whole. So let's do it again. Select the arc, click down, stick with by size with 0.001 as we did in the previous one, and click done. OK. So you can see there is no difference so far. Now, it makes sense that if we are making it denser, the mesh around the hole, we should make denser the mesh in the sides next to the hole. So let's do it. So this is what we need to do. We're going to click to use a single bias. And when we click done, OK, let me see. Let's do it again. I forgot to click where we want to mesh. So we need to click, let's say, this side, right? And then get back and then click done. And this window will allow us to set up by the number and the bias ratio how dense we want the mesh. So let's say we want 40 elements, but not uniformly distributed along the edge. We want that more elements are assigned next to the hole. So let's increase the ratio, the bias ratio, to 10. And let me do something before continue. You can see how the mesh is going to be denser by following this arrow, this red arrow. Okay? If we want it in the opposite direction, we just need to click flip, and it would be in the opposite direction. Okay? So let's get back to the original one, and then click OK. Now you can see all those purple nodes, how dense is the mesh around the hole. Let's repeat exactly the same procedure for the bottom side. So select the side, done, 40 elements, keep the same bias ratio, and OK. So it's done. Let's go to the mesh controls, which is clicking this assign mesh control icon. The element shape is going to be quad as well. All right? We're going to click structure, and then OK. Let's assign a type of element.
I have a question. Why did you have to click structure?
Because you want a specific, you don't want that the program define arbitrary geometry for your elements. You want a well-defined mesh with some topologies like triangles, for example, or squares. Okay? All right. So in this case, we're going to change respect to the earlier example plate to quadratic order. So our shape functions now are not linear anymore, are quadratic. And we're going to repeat, we're not going to change the family for the element type. It's still quad. And this time, the element type changed to S8R, because we have 8 nodes to define the element. Click OK, and mesh. the mesh looks different. Okay? If we go to the neighbors to the hole, you can appreciate that it's different from the previous example. All right? Let's compare. Both. Yes?
Do we define mesh to be rectangular? Did we do that?
Excuse me?
Did we define mesh to be rectangular?
No. The structure decides from a range of well-defined geometrics. He defined what is the best for your geometry. Okay? It'll define by itself. Depend on what? In the number of nodes and how dense you make the mesh at the edges around the hole. Okay? Yes?
Isn't it that two opposing sides don't have the same number of nodes?
Excuse me, can you say again? Can you speak up?
So two parallel sides don't have the same number of nodes. Isn't that the reason like the bottom is a little skewed?
In the bottom, for the left or for the right?
For the right one and the bottom right.
Bottom right.
Okay.
We have 6 minutes, so can we take that question
I'll
next?
ask later.
Okay.
Maybe 6 minutes.
Yes. All right. So this is the mesh. Let's continue and create a job. To create a job, we need to go to the toolbox area. We need to click here in this icon. Let's name this job just plate 3, just for the name. Continue. Click OK. Let's submit the job. So go to the job manager. Submit the job. If you want to follow the analysis, you can click on monitor and you will be able to follow here. In this case, it's running the analysis. Hopefully, it's going to complete successfully. It's good? All right. So let's see the results, what is our interest. So click on results in the job manager. Let me rotate this. Okay. This is the results. More interesting that the picture, let's see the deformed shape. It looks like that. If we want one of the stresses, we can just select one of the stresses here, and you will see some colors around. But I want to show you something more interesting. Let's see the numbers, okay, about this. So let's get back to the undeformed shape. All right. Let's go to Tools, look for Path, create a path. Let's say that is path number 1, Node, Continue, click Add Before, and we're going to select the nodes of our interest. So let's start with this plate here. This is the first node. We want this one. Is the first node we want. This is the second node we want information for. Let's check how's a node. What is the information for a node in the remote side? Now let's repeat the same for this plate. This node, just for comparison. Click Done. You can identify which nodes relates with each plate. Just OK. Go again to Tools. Go to XY Data. We are creating a kind of report. create, click on path, continue. Here, we made our path based on the undeformed state, so go to undeformed. We are going to follow for the x values the sequence of the ID nodes. Click on fill output. Select the variable of our interest, which is S11 in this case. OK. Save this as S11. Repeat the same procedure for S22. Save as S22. And I think we'll be done. Basically, what we're doing is this. If you click plot, you can see the stress versus at each node that we previously picked or selected. OK? So just click this, generate the report, go to report, XY, click on XY, go to setup here, name your report, plate 3, go back to XY to the tab XY data, click on S1, apply, because we are selecting that variable for that result for the final report. Select S22, apply again, and a report is created in that temp file, in temp folder, sorry. So let's go and look very quickly for the report. This is what is displayed, okay? So I already arranged this data in a slide, so let me get back to the slide so we can compare. So this is the last slide I have. Okay? So this is the last slide. So you can see that for the plate number 1, the first 2 nodes are the one on the top in the A location. The second node was the one in this location, which is B. And you can see that for the first plate, we should expect that the stress S11 at the A location, what it means here, would be 3 times the remote stress. This is based on the elasticity theory, right? But it doesn't happen for the first plate. But it happens for the second plate. Look at this. Node number 4 for the second plate. I mean, it's not 300, but it's the best we can get. It's an approximation method, right? So 294, which is basically 3 times the remote stress we apply. You see? Something else. How is the stress at point B for both plates? It should be S22 should be minus the remote stress. Okay? For the first plate, we have minus 26, which is totally off, right? But for the second plate, we have that the node 5, which is at this location, we have minus 82. It's quite close. It's not exactly 100, but it's close. All right? So you can see that by improving the meshing, improving the meshing for the second plate, make it denser around the hole, and changing the geometry for the shape functions, it helps us to get more accurate results. So yeah, I think with this, we'd end the presentation. Okay? Thank you.